This section of the book is on work and energy. Work has a technical physics definition that doesn't correspond to how we talk about work in everyday speech. For instance, we'll see that if you just hold a heavy weight in your hands without letting it move, then you feel like you've done a lot of work because we have this tendency to think of work as corresponding to force exerted over a period of time. In fact, that's not the correct technical definition. Work is not force exerted over time, it's force exerted over distance, or really over a displacement. It's true that you could talk about, there's still work involved in holding a weight at a steady location because what's holding it there, the atoms in your hand, are bouncing up and down and hitting the atoms in the weight, and so there is force being exerted and something's moving. But in general, you shouldn't, I don't know. In general, you just should try to stop thinking about work as force exerted over time. When you're in a physics or mathematics class, you need to think of it as force over displacement. Work, in a sense, is equivalent to energy. Work has energy units. We typically talk about work and energy as though they're different. We say it takes energy to produce work. Sometimes we say you do some work and it gets transferred into energy of some kind. So really there's a work-energy equivalence, even though we use the two words differently in English. So we're only going to deal, we could do this with vectors again, but instead in this book we're only going to deal with work in a straight line. So we're going to assume we've got some object that is constrained to moving in a straight line. So I'll just draw a block on the x-axis. I'll label it as m, as though it has some constant mass m, and may refer to it as just a mass. Mass m, and we're going to have a force that acts parallel to the axis along which m moves. So either the force will push to the right, or it might push to the left. But the point is that the force needs to be parallel to the displacement. I'll go ahead and say what you would do. If you were using vectors and you had more general forces and displacements, you only take the component of the force that is parallel to the displacement, and that boils down to taking a dot product, which you'll get to in multivariable calculus. But right now, in this setup, if the force is constant, if F is a constant force, and normally force is a vector, but since we're talking about force in a straight line, the direction of F will be encoded in whether F is positive or negative, so I'm not putting a vector symbol over F. If F is a constant force acting on M, and as M moves from some initial x-coordinate, x0, to some final x-coordinate, x1, then the work done by F on M is just F times the displacement. So F times delta x, where delta x is this change in the x-coordinate. So the displacement. Note that it's displacement, not total distance traveled. We don't know whether we're only talking about the x-coordinate where the mass starts and where it ends up, not what happens to it in between. That's because Work will occur with a sign. If F is positive, so think pushing to the right, and the displacement is positive, so the net change in X is to the right. So you think if F and the displacement are in the same direction, then the work is positive. If F is negative and the displacement is negative, so F is pushing in the negative direction, but your change in position is in the negative direction, you get positive work again. You get negative work, though, if the force is in a different direction from the displacement. All right, fine. So this is just the definition. And what it means, and I'll say it again, is that one of the things it means is that if there's no movement, then there's no work done. So technically, if you're just holding a mass steady, even though it might take some effort to hold it steady, technically it takes no work. All right, great, but this is a calculus class, and we're not terribly interested in the case where F is constant and you just multiply times the displacement. That case is important, it comes up, but it doesn't require calculus. What does this have to do with integrals? Well, what frequently happens is F is not constant. F is a function of the position, so that F is a function of X. So what frequently happens is F, the force acting on M, is a function of the position. So that as the mass moves, the force can be changing. Well, then how do you calculate the work done by this variable force? Oh, I should say something about how we speak. Technically, you can say that the force does the work. In normal speech, if the force is being exerted by, for instance, me, I would say I do the work instead of the force that I exert does the work. I would just say I do the work, or Sally does the work, or some other object or person or whatever agency does the work, whatever is producing the force. So if I say like you or a person does the work, understand technically I mean that the force that the person exerts does the work. All right. So how would you find the total work now in displacing the mass from x equals x naught to x equals x1? Well, we do what we always do. We chop up the x-axis into lots of little subintervals, delta x. And on each subinterval delta x, you assume f is constant or roughly constant. And you take Riemann sums and take limits. But we're used to talking infinitesimally now. So the infinitesimal amount of work, dW, the infinitesimal amount of work in displacing it, some infinitesimal dx is f of x times dx. And so the total work is you integrate as x goes from some initial x coordinate to some final x coordinate. You add up you take the continuous sum of all these infinitesimal contributions of work. So you integrate the force with respect to infinitesimal changes in the x coordinate. This is what we're going to look at first. We will, at the end, get to some problems where, in fact, it turns out that instead of thinking of f as a function of x and multiplying times small changes in x, and this will look a little strange, instead we will see that, well, in some problems, it's kind of nicer to think of x as a function of f and instead take x times infinitesimal chunks of force. So this, well, we'll see where this arises, but at first we're going to think of force as a function of x, and so for a small change in x, you multiply times the force, but later we're going to do problems where the displacement of an object depends on kind of the force that's acting on it. We'll see how that can possibly occur. And then we'll use that dw as x times df. All right, this is work. What's a typical problem? There are, let's see, there's some numbers I want to use, a specific example. So I should talk about the units of work maybe before I do an example. The units on work. Well, it's force times distance units. Force units times distance units. So in the metric system, you would have 1 Newton meter, not Newton per meter, Newton times meter. Force times distance. This is given a name. So this is 1 Newton meter. This is given a name. This is 1 joule. So I'll say it again, work is a form of energy. So work and energy are equivalent, so that's an energy unit. In the English system, it's 1 foot-pound. Here you say the distance unit first and the weight unit second. I don't know why, but everybody says a foot-pound, and that's just what it's called, a foot-pound. There's no specific name for that. All right. I've decided that I should make a comment about the example that I'm about to do. This is a classic example of a bucket that's being raised at a constant velocity and is leaking sand. Some books it's sand, some books it's water. All of these books do these problems without commenting on the fact that the mass of the object you're talking about is changing. Well, they comment on that, of course, as part of the problem because they're trying to do a work problem, and so the force that's being exerted, there's the force you're exerting and the force of gravity. So they comment on the fact that the mass is changing, but they don't comment on the fact that what that does to Newton's second law of motion. Newton's second law of motion, that the sum of the forces equals the mass times the acceleration, is true if the mass of the object is constant. But in this problem, the mass is explicitly not constant. And so you should wonder, just because the velocity is constant, so in the problem, the velocity of the leaking bucket will be constant. So there's no acceleration. Does that mean that the net force acting on the bucket is 0? Well, if you have F equals ma, so if mass is constant, the net force is the mass times the acceleration, so the mass times the rate of change of the velocity. And if the velocity is, by the way, the velocity, we always mean the velocity of the center of mass when we say the velocity of some object, now that we know what center of mass is. So that, or you can think of it as a point mass, but that would be a little strange for a bucket of sand. If the velocity is not changing, this should be 0, but this is if the mass is constant. Now, even when the mass is constant, you can pull it inside the derivative and write the net force as the rate of change of mv, the momentum of the object with respect to time. And there are problems where, and we've talked about this before, there are problems where the mass of the object is changing and you continue to use that the net force is the rate of change of the momentum with respect to t. But now if the mass is changing, the product rule comes in. This applies when the object is actually ejecting mass or kind of smacking into mass that's being added. It applies when, from your point of view, the mass that's being added or the mass that's being subtracted has 0 velocity. So when hail drops through the atmosphere and more ice builds around the hailstone, that's essentially because the hailstone is hitting water droplets that are not moving, and they're attaching to the hailstone. so that they start with zero velocity from our point of view, the water droplets. And so this equation applies. It's essentially the same thing with a rocket expelling fuel. We kind of assume in those problems that this applies because we assume that the rocket fuel is expelled so that the mass that leaves has zero velocity as far as we're concerned. But you might think, no, it's shooting out of the back of the rocket. But so yes, it has velocity relative to the rocket, but from our point of view, we think of the mass as just kind of still and that it propels the rocket along. However, in the leaking bucket problem, it is most physically reasonable to assume that as the bucket rises and the sand leaks out, that instantaneously as the sand leaves the bucket, the sand is moving upward instantaneously at the same rate as the center of mass of the bucket. And after it separates from the bucket, then it starts to decelerate under the force of gravity, since the force that we're exerting on the bucket no longer applies to it. In the case where the mass that's attaching or detaching from your object is instantaneously moving at the same velocity as the center of mass of the object, then it's still true that F equals ma. So that in this problem that I'm about to look at, where the acceleration of the object is zero, that will mean the net force is zero, so that the force that we're having to exert is exactly negative the force of gravity. I've added a long comment about this to the end of this section of the book, so if you want to read more about it, go ahead. But if it occurs to you to worry about Newton's second law and the changing mass, understand it's okay in this problem because we're assuming that the mass that's leaving the bucket does so instantaneously at the same velocity that the center of mass of the bucket is moving. So, now let's do an example. So, suppose you've got a building and you're lifting some bucket. Here's one of my great drawings. There you are. Or it could be a crane. One of your arms is seemingly much longer than the other one. And actually, that wouldn't be how you'd lift it. You're lifting a bucket of sand. So you're lifting the numbers I want, a 20 lifting a bucket of sand. 100 feet at a rate of 2 feet per second. We're going to initially lifting a bucket of sand at a rate of 2 feet per second. Initially, there are 20 pounds of sand, but sand leaks out at a rate of 1/100th of a pound per second. And we would like to find the total work done on the bucket of sand as we lift it up the 100 feet. Or you could say, how much energy does it take to lift this bucket of sand whose weight is changing as we're lifting it 100 feet? If the weight were not changing, understand this would be a completely trivial problem if the weight were not changing. If the weight were always 20 pounds, so there's no leaking, and you raise it 100 feet, well, the weight is force, the force that gravity is exerting on it. So for us to lift it at a constant velocity, we have to exert the same magnitude of force upward. So the force we're exerting is in the direction of the motion, and we're moving at 100 feet. So we would take 20 pounds times 100 feet and get 2,000 foot-pounds of work. But the weight is changing. And so the force that we're having to exert is changing because, I'll say it again, because we're moving at a constant velocity. There's no acceleration. And by Newton's second law, the force that we're exerting has to be counteracting the force of gravity, which is the weight. But the weight's changing. All right. So how much work is done? In lifting the bucket. Of sand. All right. So the force that we're exerting, say it a third time, because the velocity is constant, the force that we're exerting has to have exactly the same magnitude as the gravitational force. So it's the weight. Which is changing. First, I'm going to write the weight as a function of time, and then we'll have to change it to a function of the position. So I'm going to call my vertical axis, you can call it x, y, and z are common for vertical axes. Why don't we call it y? And I'm going to assume I start at y equals 0. So I'm just calling where the bucket starts at 0. So this is the y-axis. And we're lifting the bucket, which suddenly is very large. We're lifting the bucket upward. I'm first going to write this as a function of time, and then we'll have to convert it into y coordinates. So f at time t, where t is in seconds, is, well, there's the initial 20 pounds. There's the initial 20 pounds, but for every second that goes by, we're losing 1/100th of a pound. So the weight as a function of time is this. And the weight is the force we're having to exert upward to counteract gravity to make the velocity constant. So here's the force as a function of time. Well, we need everything in terms of the y-coordinate. What's the y-coordinate as a function of time? Well, the y-coordinate, we're lifting the bucket at a rate of 2 feet per second. So it's 2, so this is pounds, 2 times t, feet. Right, calling the initial position of the bucket 0. So this is what we get, that the force as a function of time is 20 minus 1/100th t. On the other hand, the y-coordinate is 2 times t. If we solve for t, we get, and substitute it in, so t is y over 2. So as a function of y, the force as a function of the position is 20 minus 0.01. So maybe I'll write that as 1/100th. 1/100th, and t is y over 2. So we get this. This is still in pounds. So y, we get f of y is 20 minus y over 200. Okay, pounds. So the work, total work that we do in lifting this, you integrate as your y-coordinate goes from 0 to 100, f of y dy. This is an easy integration problem now. So the work is the integral from 0 to 100 of 20 minus y over 200 dy. This is just the power rule. So we get 20, for an antiderivative, we get 20y, and then you get a y squared over 2, and then times divided by 200, so we get a y squared over 400. And you evaluate as y goes from 0 to 100. At 0, you get 0, so we get whatever you get at 100. So we get 2,000 minus 100 squared over 400. You can divide out one of the hundreds, and you get 100 over 4, so that's 25. So we get 2,000 minus 25, so we get 1975. 1975 what? Foot-pounds. That's how much work it took, or how much energy it took to lift that bucket of sand. 1975 foot-pounds. Notice that, yeah, if the force had been constant, the bucket had not been leaking, here's the 2,000 it would have taken, but it took 25 less than that because we were lifting less sand as the sand leaked out. All right, let's do another problem. Another standard kind of variable force problem where you are interested in the amount of work relates to springs. So there are a lot of physical situations which behave like a mass on a spring. We actually don't care about the mass, but it gives us something to have attached and something to push on that you think of pushing on instead of just pushing on a spring. But really, the mass is irrelevant in this problem. Suppose you've got a mass connected to a spring. So here's a spring. If there's no, so we're looking at horizontal motion, so gravity doesn't have any effect on the discussion of what happens horizontally. If there's no other force in the problem, then the mass will just sit there at the spring's natural position, and we call that the equilibrium position, and we always make that x equals 0, the equilibrium position, where the mass would just sit motionless in the absence of any external force, equilibrium position. And then we're going to assume that our spring obeys Hooke's law, which is approximately true for real-life springs. And it says that the force that the spring exerts is proportional to, but with a negative sign here, where k is greater than 0, and this k is called the spring constant. It depends on the physical characteristics of the spring. So what does this mean? You may have looked at Hooke's law before. It means that if you displace x, so if x is positive, the force that the spring exerts, it tries to pull you back. So the force points in the opposite direction. So it's negative. Yeah, if x is positive, k is positive, then this explicit minus sign makes x negative. On the other hand, if you compress the spring, then the x-coordinate, so you push the mass over here, then the x-coordinate is negative. So this would be negative, positive, negative. The force would be positive, right, because the spring would push back that way. So this is Hooke's law. And it's kind of a standard setup for having a variable force acting on something. So a typical question. So an example. How much work does it take? Oh, how much work does it take to compress a spring with spring constant, just make up a spring constant. (10 newtons per meter). How much work does it take to compress a spring with spring constant, 10 newtons per meter? 0.5 meters. So you've got a spring. You're told it's spring constant. It's 10 newtons per meter. And you're asked how much work does it take to compress the spring 0.5 meters from the equilibrium position. This is, you can draw a picture and it might help you think about it, but it doesn't take too much. So we're going to apply a force in the negative direction, thinking of positive x's to the right. We're going to apply a force in the negative direction to displace the mass in a way that compresses the spring. So to displace the mass to the left. So the displacement will be negative, the force will be negative, and so our work will come out with a positive sign. The work that the spring does during that time, we would consider with a negative sign because the spring will push in the opposite direction from the displacement. So the work that we do is positive in this setup. The work that the spring does would be negative. Okay, so this is the force that we're exerting. All right, F, us, or me. The force that I'm exerting, as opposed to the force the spring is exerting. Okay, the force that I'm exerting, we can talk about, it turns out that this is independent of how fast you compress it. We'll see that in a minute, but you can always imagine that you're compressing it at a constant velocity, so that the force that I'm exerting has to be negative the spring force, so that the sum of the forces is 0, so that there's no acceleration, so that I just do this at a constant velocity. In which case, the force that I have to exert is k times x. All right. And the work that we do then is we want to compress the spring. So we're going from x equals 0 to x equals negative 0.5 meters because we're pushing it to the left. The force that I'm exerting is negative the spring force. So is negative the spring force. So it's this is fine. Let me drop the units up there. The spring force is kx. So all right, it's the force that I'm exerting times dx, and you add those up. But that's kx, so it's the integral from 0 to negative 0.5 of kx dx. But we know k. We're told that k is 10 newtons per meter. I'm going to drop all the units. They're consistent. I'll put them in the end. They'll come out in joules. You get 10 x dx. All right, so how much work do we do? The integral from 0 to negative 0.5 of 10 x dx. That's just the power rule again. You get 10x squared over 2. You evaluate from 0 to negative 0.5. So you square negative 0.5, you get positive 0.25. So let me just write this as 5x squared. We get 5 times 0.25 minus 0. So we get 5/4 or 1.25 Newton meters, but that's a joule. That's the amount of work it takes to compress the spring. Okay, great. So that's these are standard basic problems of integrating force as a function of the position. I would like to look at kind of kinetic energy and potential energy. You may know what those terms mean, but you may not. So let's suppose you have a constant mass m, so the mass is not changing. And the sum of the forces acting on m, so there's all the forces. Okay. All right. Suppose you're in this situation. Well, then you know Newton's second law. Newton's second law of motion tells you that the sum of the forces is the mass times the acceleration. This is m times the derivative of the velocity with respect to time. But now I'm going to do something a little unusual. I'm going to use the chain rule and write dv dt is dv dx times dx dt. So thinking of motion along the x-axis. Remember the chain rule in this Leibniz notation looks like cancellation of fractions. So dv dx times dx dt, it's like the dx's cancel, and you end up with dv dt, right? But dx dt is the velocity. And so we end up with m dv dx times v. So what? So I'm going to write that. I'm going to move the v, but we get mv dv dx. All right, why do we care? All right, now let's imagine that we're looking at the motion of this mass and we're looking at the work. The work done by F on M between, well, we could say between two positions. Position is also a function of time. I'm going to write everything in terms of times just because it's easier to talk about, although I'll have to write more notation then, is what? Well, it's the integral, and I'll write as t goes from t0 to t1. Of course, if you wanted to evaluate this integral, you'd need to know what the position is at time t0 and what the position is at time t1 and write the x-coordinates of the position there. But what we've just said is that this is equal to, well, F is m dv dv dx times dx. Now, the chain rule in integration terms, or substitution, which is the same thing, says that effectively these dx's cancel. And you get that this equals whatever the integral as time goes from t0 to t1 of mv dv. But m is a constant, and the integral of v dv is v squared over 2. This is mv squared over 2, evaluated between t equals t0 and t equals t1. And normally, so that means that you get m times v1 squared over 2 minus m times v0 squared over 2, where v1 and v0 are the velocities at times t0 and t1. So that, in fact, I could have written x0 and x1 here, and then switched to t0 and t1 in between and ended up with, all right, so what does this say? It says that the work that you do goes into this change in mv squared over 2. Well, you may or may not have seen the definition of the kinetic energy of a mass, but kinetic energy of m is 1/2 the value of the mass times its velocity squared. So what this says is the work done by all of the forces acting on a mass gives you the change in the kinetic energy. Well, that's kind of cool. So the work done by the total forces acting on m equals the change in kinetic energy. So the change in 1/2 mv squared. That's really cool. All right. That's really cool, and you may have noticed it wasn't particularly difficult to show. So that's another cool thing. All right. What's potential energy? Actually, potential energy has different meanings depending on what's causing the potential energy. You need some ambient force field around, and it needs to be something that's technically called conservative. But there is one ambient force field on Earth that we deal with all of the time, or actually near any mass. So we're going to talk about gravitational, but I won't say that since most of the time, since it's the only one we're going to talk about. What's gravitational potential energy? Let me say what it is kind of intuitively, and then we'll see mathematically where it comes from. If I lift like a coffee cup up in the air, we say that I've given it potential energy. What do we mean? I mean that if I let it go, it's going to move. It's going to start moving, we think on its own. Of course, it's due to gravity, but gravity kind of, it's surrounding us. So we got to think, if I let it go, it's going to start moving, and its height that I've lifted it to is going to be converted into kinetic energy, the 1/2 mv squared, as it falls. And so it's going to start moving faster and faster as its height decreases. And so since when we let it go, it gains kinetic energy, 1/2 mv squared, we say that it had some energy to start with that's converting into this kinetic energy. And that's the potential energy, the energy that's stored in the coffee cup by lifting it. What on earth does that mean? So I had to do some work to lift the coffee cup against gravity. So the work that I exert, the force that I exert is one force acting. So you lift a mass, m. So here's some mass. Gravity, I'm going to take upward as my positive direction. Gravity is pulling downward. I am pushing upward. So the sum of the forces acting on the object, my coffee cup, so the total force, F, acting on M, is the force that I exert minus mg, where g is the gravitational constant in metric units. It's approximately 9.8 meters per second squared, or meters per second per second. In English units, it's about 32 feet per second per second. So g is approximately 9.8 meters per second squared, or 32 feet per second squared. So the total force acting on M is this. But if I start with my coffee cup or whatever the mass is, if it starts out with 0 velocity and I lift it and hold it there so it ends with 0 velocity, then it started with no kinetic energy, it ends with no kinetic energy. But what we just saw a minute ago was that as I lift the mass from some initial height, some initial y coordinate, to some final y coordinate, actually I don't need to, of the total force, F, acting on this, this is the change in the kinetic energy. But assuming that I start with no velocity and end with no velocity, this will be 0. So I'm assuming zero initial and final velocity. Actually, all that's important is that the initial velocity and the final velocity are the same, or actually are the same after squaring, but typically you think of something's at rest, you raise it and it's at rest, and final velocity. Great. So that's 0. So what does that mean? It means that this integral is 0. But now you put back in that this is the force I'm exerting minus the force of gravity, which is constant. And so this is 0. But then you can separate these two and do the integrals, and what you get is that the work that I do, so the force that I exert on the mass, equals the integral from y0 to y1 of mgy. But mg is a constant. This is just mg times the change in the y coordinate, y1 minus y0. So how much work do I do in lifting the mass kind of against the force of gravity? It's this. So the work that I do, or the work that you have to do, this is just mg times the change in the y coordinate. So the change in height. And this is called the change in potential energy. And you have to actually have a potential energy, you have to set where you're calling potential energy 0. In gravitational problems, that would normally be on the ground, so that would be where y0 is 0. So we normally take potential energy just to be mgh, where h is the height. And so, right, that's potential energy. And what does that mean? It means that if we raise something up to a height h and we let it go, when it falls, all of that, then the sum of the forces acting on the mass, there's only one, and it's gravity. And as we saw a minute ago, all of that, the work done by gravity as the mass falls, will get converted into kinetic energy. And so all of this will equal 1/2 mv squared, where v is its downward velocity at any time. All right. That's the explanation for the connection between work as the integral of force times displacement and kinetic energy and potential energy. I want to look at a couple of problems where you want to set them up as the integral of x df, not f dx, and then that will be it for this section. So how do you get a problem where you should kind of think of the distance that you have to move a mass is a function of the force that's acting on it? It's not exactly how you think about it, but that's how the integral sets up. So this is a standard example. I need that the weight of water, I'm going to use that the weight of water is, but really it's only approximate, of course, equals, and I need to look, it's 62.4 pounds per cubic foot. All right, so what's a typical problem? Well, maybe you've got a tank that's a right circular cylinder. I'm going to assume its radius is 8 feet. It's 100 feet tall. So this is a tank. And it's got 20 feet of water in it at the bottom. That doesn't look like it's 1/5 of that, but I wanted to draw it higher. So here's 20 feet of water. And a typical question would be, how much work does it take to lift the water think pump maybe, out of the tank? Now, you have to say some extra words here. So what do we mean? I mean, how much work does it take to lift all of this water up this 100 feet? And then maybe you slide it off to the side, or you do something that doesn't take any work because you only have to counteract gravity. There's no problem at the side. So we're going to lift this, each part, up 100 feet. The problem is you don't want to just take this and lift it up 100 feet, because then you will have lifted this top part 120 feet. You don't keep the water stacked up on itself. You're lifting the water up. You can think of taking the top part first and the lower part second. Of course, maybe what's happening is there's a pump at the bottom, but you can think of taking each slab and lifting it up. All right. why is this kind of a variable work problem? Why does this require an integral? The problem is that, or the issue is, is that if you take an infinitesimally thick, so an infinitesimally high little slab of water, the distance that you lift this piece, so this one's at like 20 feet from the bottom, the whole tank is 100 feet, you only have to lift this part 80 feet. On the other hand, you have to lift the part at the bottom 100 feet. So the distance that you have to lift each thing changes as you're looking at different chunks of volume. Each of those volumes has weight. So as you change the weight that you're looking at, this piece versus this piece, the amount that you have to lift it changes. So that's why you're thinking of the distance you have to move each piece is a function of which piece you're looking at, so which weight you're looking at. And so this sets up as x times df. That is, we're going to use that the infinitesimal amount of work that we have to do on each piece is how far we have to lift it times df, where df is the infinitesimal weight of each little piece. So this is infinitesimal weight. Aside from that, the problem's not too bad, although people get confused about the limits of integration versus how far you're lifting things. So let's see what happens. So what we will do is integrate. Something like this. Well, I've already written x, so maybe I will continue calling it x. That means my x-axis is the vertical one. Fine, I would have preferred calling it y or z, but I already wrote x. So we'll set up the x-axis there. I put x here. It's not just x, it's, it will be in terms of x, but it's some kind of distance that you have to, or so displacement, that you have to move each slab through. And it will be in terms of x, but I shouldn't just call it x because this slab is at x equals 20, but you move that one 80. So you need to be a little careful, or actually you need to be very careful. The work equals the integral. And the way I've got it set up, what you want to do is add up all the little contributions of work involved in lifting each of these pieces. So you add these up as x, so x encodes which slab of water you're talking about. We want to do this for each slab of water as between x equals 0 and x equals 20. So those are your limits of integration. Your limits of integration are keeping track of the pieces that you're summing over. And so as x goes from 0 to 20, we want to add up all the little contributions of work for the slabs at the different x coordinates. Yes, the distance might be 80 or 100 that you're lifting a slab through, but we're doing this for the slabs between x equals 0 and x equals 20. This is part of the confusion. Then we'll have a df. That's the weight of a slab at x coordinate x. But there's the distance, and how far do you lift it? So when you're at a given x coordinate, you may have figured this out already. When you're at a given x coordinate, so here we are at some x coordinate, how far do we have to lift this piece in terms of x? Well, this distance from the bottom to the top is 100. This distance is x. The amount you have to lift the piece at coordinate x, 100 minus x. Right? So, for instance, the piece that's at x equals 20, you only have to lift it up 100 minus 20, 80 feet. The part that's at x equals 0, you have to lift up 100 minus 0. So yeah, that's 100 feet. What's df? df, this is the weight of the little slab at x, the infinitesimal weight. But I remind you, I just erased it, but water weighs roughly 62.4 pounds per cubic feet. Now pounds, that's weight, but we need to multiply times volume. So this will be, this df is the 62.4 pounds per cubic feet times volume, times the infinitesimal volume. So I'll put that in. You know, you break up these problems into manageable pieces. I'm dropping the units in the integral, but everything's going to come out in foot-pounds. All right? So, okay. So, but what's dV? Now that depends on the shape of the tank. It's a right circular cylinder, so it's the cross-sectional area times a little change in x. The cross-sectional area is just pi, the area is pi times the radius squared. And so dV you get the 62.4, and dV is, actually let me give myself some more room. So we get the integral from 0 to 20, the 100 minus x, the 62.4, and then dV is dA times little dx, is A times little dx, but A is 64 pi times dx, right? This is the cross-sectional area times dx to give ourselves a little chunk of volume. And I'm not going to finish this integral, but the 62.4 and the 64 pi are constants. You just pull those out. You integrate 100 minus x with respect to x. That's easy, and you evaluate from 0 to 20. And this comes out in foot-pounds. Okay, what's a problem like this one that would be slightly more difficult? Well, our cross-sectional area was constant because we were looking at a right circular cylinder. We could set up the exact same problem with some strange conical tank that, I don't know why you'd use a conical tank, but hey, you could have a strange conical tank, and I won't even draw any supports for it. It'll look like it's balancing on its point. So another example would be kind of the exact same problem, except now, strangely, your tank is a right circular cone. We'll still say it's 100 feet tall. We'll start with the same problem that you have 20 feet of water that you want to pump just up to this height and maybe slide it off to the sides or something. We just want the work involved in lifting this water up to this height. And again, the problem is the same, that the amount that you lift different pieces varies, so that we need to do an integral. So the work involved in lifting the water, the initial thing that you'd write doesn't change. It's still, we would let x go from 0 to 20. We let x run through the places where we actually have some water, so that x is encoding, we're looking at this chunk and how much work we get from lifting this infinitesimal slab. So you let x go from 0 to 20, and it's still the distance that you move it, right? We don't have to worry about the difference between distance and displacement. We're lifting it up and not back and forth. So the distance times little change in F. It's still true that the distance you lift the slab at X is what it was before. If you've got a slab at X, you have to lift it up to the top, so that's 100. That distance is 100 minus X. That doesn't change. dF, it's still true that this is the weight density of water, so the weight per cubic foot, times little chunks of volume. And little chunks of volume are still cross-sectional area. Right? Understand the parts of this that are the same. It's still the cross-sectional area at X times a small change in X. The difference now is that the cross-sectional area changes as X changes. It is not just some constant like pi times 8 squared. How do you figure out this cross-sectional area? Well, your cross-sections are still circles. It's just that the circles are getting smaller. Let me draw a circle up higher where I can draw something bigger. You need to know this radius as a function of the x-coordinate. The radius of the circle that's up here at x-coordinate x, you need to know what that is as a function of x. Because the cross-sectional area is, well, the cross-sections are still filled in circles, so disks, technically. So you can replace a of x by pi r squared, but that just, this kind of puts off your problem a little bit. You have to put in what r is in terms of x. It clearly changes as x changes. How do you do that? Well, you may have seen it already, but use similar triangles. You look at this big triangle, this big right triangle that has 8 here and 100 here. And then there's this smaller triangle that's similar to it right here that has r and this is x. And so what we get is that I'll take the ratio of this to this, so we get x over 100 has to be equal to r over 8, which means that r is 8x over 100, or if you prefer, divide numerator and denominator by 4, 2x over 25. Okay, so that's what you get for r as a function of x, and you put that in right there. So r squared becomes 2x over 25 squared dx. This, again, would come out in foot-pounds. This integral is also not difficult. You still you can pull out the 4 over 25 squared, the pi, and the 64.4. You have 100 minus x times, you'll have times x squared. You multiply that out, use the power rule twice, and get whatever you get. The big difference between this and the last problem is just this part. The cross-sectional area is changing, so your formula for dv changes, which changes df in the work integral. But you calculate this, and you get whatever you get. In the next section, we're going to look at hydrostatic pressure. That'll be our last big example of applications of integration, and after that, we'll have to start our discussion of polynomials and infinite series, which will be completely different from all of this stuff that we've been looking at.